Thanks, Jeff, and thanks everybody for giving us an opportunity to share some of the work we've done. First, I need to acknowledge a couple of our authors here on the PowerPoint, and it's Reed Hawkins, who's a SUE in Wilmington, and who's our collaborative investigator for this part of our CSAR project, and David Glenn from the Morehead City office. The title screen there shows a figure, which is an NDFD forecast of winds associated with Hurricane Sandy last fall, as the storm was forecast to move onshore across southern New Jersey. And the shading there represents the wind speed from the NDFD, as shown in this image from the New York Times. And it's pretty obvious. You'll see some of the discontinuities in the wind speed colors and shading. Those result from the differences in WFO boundaries. And that's one of the things that we've noticed and we're working on in this project in terms of trying to improve. There's an outline of a little presentation this morning. We're just going to talk a little bit about the project itself, some of the deficiencies in wind forecasts and tropical cyclones in the GFE era, the methods and results of our project, and kind of how we tried to roll that into operations, at least experimentally, this past year. Just a real quick background on our project. The CSAR project was a 3-year project. It's actually, the funding for that has completed, but we're still doing follow-up work on it. A portion of that project was to improve the forecast of wind and wind gusts associated with tropical cyclones. Bryce Tyner, who was is a graduate student at NC State, he worked on a key part of that, which looked at verifying NDFD winds, looking at some larger scale patterns in terms of climatologies and things like that, and also evaluating the TCM wind tool wind vortex pattern within it. As a side project, Reed and some of the other folks and I worked on trying to look at some of the wind gusts. And our projects also had some support from the NOAA Hurricane Conference, and a little map to the right there shows shading of or circled in areas of WFOs participating in this part of the project. In terms of deficiencies in creating wind forecasts or wind gust forecasts specifically with tropical cyclones, there's a very long list there, and I'm sure many of the forecasters on the call today can provide many of these and may have others. But just to hit the highlights, there's still lots of gaps in our understanding of the spatial and temporal resolution of the wind field, and specifically wind gusts associated with tropical cyclones. And in addition, results from previous studies, many of which have failed to really taken root in the operational forecast setting. So there's a lack of utilizing previous research there. As a part of the project, we surveyed numerous forecasters in the Southeast to kind of see how they created their TC wind gust forecast, and we heard a wide variety of methods they use, from using multiplication or product factors to adding raw values to guesstimates and things like that. And many of those methods lacked consistency and good science. One of the more typical methods that forecasters use was using something called a Gust factor, which essentially is just a multiplier to use with the sustained wind to produce a wind gust from it. So we'll show some examples of that. But even with the Gust factor, the logic and the values range wildly from office to office, and with even in offices. And GFE tools themselves are often inefficient or even deficient. And there's limited collaboration between office to office, limited shift-to-shift continuity or consistency. And all this ends up resulting in an often inconsistent process that's poorly collaborated with limited science, which typically, or not typically, but can often result in an inaccurate and difficult forecast for users to use. So our project specifically, we examined the sustained winds, the wind gusts, wave heights, and gust factors for 10 tropical cyclones that impacted the Carolinas and Virginia. In the bottom center of the slide, you'll see the map of the tropical cyclones that we examined. We examined both land and marine observations, and for each of those, we computed a gust factor which essentially is just the ratio of the wind gust to the sustained wind speed. A table of the storms we examined is shown in the lower left, and a map of the observations used in this study is shown in the lower right, which includes mostly land-based observations, but we did use buoys where possible. So specifically for the land locations, we used observations from ASOS and AWOS sites. We looked at the hourly observation only. The stations included varied from storm to storm, but they were used and determined to capture the larger wind field in general, and we examined a total of nearly 15,000 gust factors. For marine locations, we only used observations from buoys that have an anemometer height of 5 meters, and that was to remove some of the variability from the different anemometer heights. We recognize that you can do some reductions and try to standardize those, but that was kind of beyond the scope of our project to look at other heights. We tried to take a simple approach there. And also, we only used observations in which the wave heights observed were less than 5 meters. And we did that because there's a fair amount of uncertainty in the quality of the wind observations in large waves, and that results from buoys being sheltered by the tall waves around them, from the buoys not being upright and at a significant angle, and that tends to reduce the quality of the observation. So based upon that, the marine observations only included about 1,700 gust factors. The table at the bottom shows the number of gust factors for both the land and marine locations we used. The average gust factor, which you'll notice for the land locations, was considerably higher than the marine location, and the standard deviation was much more variable for the land locations than the marine locations. And the maximum wind speeds in knots are shown there, and you can note that the maximum wind gust for the marine locations was much reduced from the land locations. Again, that's because of the 5-meter wave height boundary we put on there, so we recognize that that has some impact on the data. So real quickly, looking at the results, what you'll see here on the left side is a plot for the land locations, and on the right, the marine locations. Each dot on these scatter plots represent a gust factor with a sustained wind. The sustained wind is shown in the horizontal axis, ranging from 0 to 80 knots, and the gust factor is on the vertical axis, ranging from 1 to about 2.5. So each blue dot is either an observation or sometimes multiple observations at that point. And you'll notice for the land locations there's a tremendous variability, but that variability is larger at lower sustained wind speeds and tends to reduce in time as reduce as the sustained winds increase. And there's a general best fit curve there, which is shown and generally shows a decreasing gust factor as winds increase in speed, and that's somewhat intuitive for most of us. On the right, the marine observations are shown there, and you'll notice a much tighter clustering of observations. Also a regression curve there that is fit much more closely and also gradually, ever so slightly, increases the gust factor with increasing wind speed, but a much greater concentration and consistency in the observations there. The histogram shows a greater number of observations for the land locations, but also the bin with the greatest number of gust factors is this 1.3 to 1.4 bin, where for the marine locations it's considerably lower, with a much more rapid decay or drop-off for higher gust factors. So a much greater consistency there for the marine locations. So we plotted regression curves for each of the storms shown on the next slide, which again the land observations are on the left and the marine are on the right. The various storms are shown in the rainbow colors there, and the black line is the best fit for all of those observations for either the land or marine locations. Again, you'll see a lot of variability there in the land locations. Again, that's not too surprising given the different locations, coastal, marine, inland, different environments for the different storms and intensities, but they all show a general similar curve, and the marine locations are much more closely fit the overall line there, which is again in the black bold. And again, these kind of figures here are very consistent with some other research that is out. Now, how do we use this data set? Well, we tried a whole bunch of options, including some simple tools in GFE and some more complicated things, and we eventually settled on a more mature methodology that includes a new GFE element or grid, which we call the gust factor grid. And that essentially is a ratio between the wind gust and the sustained wind for a specific period of time. And the way we create the wind gust factor grid initially is once the winds, sustained winds in GFE have been created by the forecaster and are okay, the forecaster can use a tool which will populate the wind gust factor from by using that regression curve we saw earlier. So depending on what the wind speeds are at a specific grid point, it will match the regression curve and output the gust factor. So that's the first step, and that's the middle point here in the cartoon at the bottom. But then forecasters can then begin to edit that gust factor grid for local effects and things that they find are important. They could be increasing the gust factors on the back and southwest side of a northward advancing storm because of dry air mixing in on the backside and stability impacts. They could lower the gust factor, as we showed in this example here, in the Piedmont region associated with cold air damming. So it provides some flexibility for the forecaster to change the gust factors over spatial areas, spatially and also temporally. And then the wind gust is essentially just produced by making a product of the wind grid and the gust factor grid. And that is a very simple tool we've produced to do that. So what are some of the advantages of this approach? Well, there's a common starting point that's provided, and that's produced through those regression curves. And then forecasters can now more easily integrate boundary layer stability, other factors into the forecast process, whereas before, many times they would simply use a single value across their entire domain for much of the storm period. The grids provide a more science-based process, and we can now, almost most importantly, collaborate and see what our neighbors are doing. And in this example here, Raleigh, in the central part of the map, we can see the gust factors for our neighboring office down in Wilmington. And by doing this, the wind gust process is no longer a black box. We can visually see what our neighbors are doing, and we hope provide a more consistent output. Now, this scary-looking chart here is the actual process, but all 10 steps here are pretty much made with a hand-holding type framework. So some of these are pretty simple steps, and this is perhaps a little bit over-engineered. But what I wanted to point out is in the lower left-hand corner is a snapshot of the wind gust factor selector tool in GFE. And this is essentially what forecasters would use to initially populate that gust factor grid. And they can choose a couple options on there, with the default being the regression curves. So now, that was one part of our project, and while we're messing with this, we thought we'd try some other things and evaluate some other approaches. And another option, another item we developed was a similar methodology for actually the just wind grids themselves. And what we developed was a wind reduction factor. And I won't go into a lot of details here because that wasn't the focus of this presentation, but essentially, looking at the cartoon at the bottom, the forecaster would load the raw NHC guidance via the TCM wind tool, but they would use no reduction factor in the actual tool themselves, so they would use a slider and set that to 0. Then from those raw grids, they would remove non-meteorological features and do some broad smoothing. And then they would create a wind reduction factor grid. And again, that in the past, in the GFE tool, you would just use one factor for the whole area, perhaps 10, 20, 15%, 30%, if not more. Well, now the forecaster can then apply these spatially across their area and also have those evolve over time, perhaps as the storm structure changes, the storm weakens, and things like that. And essentially, at the end, the last step is to create the wind grid from the product of the reduction factor grid, which will be multiplied by the raw or the smooth wind grid. So that approach we've tested as well. Again, we find a lot of continuity or a lot of possible improvements with that. Primarily, forecasters, again, can integrate lots of factors into the process instead of just choosing one reduction factor. They can collaborate visually in GFE. There's shift-to-shift continuity because that grid will actually sit in there until someone touches it. It also diminishes the burdensome workload sometimes as a new TCM product is issued. And we can even load in climatological and pattern-based reduction factors as starting points as well. And lastly, the other improvement that the project is working on, just to hit on real quickly, is trying to improve the actual TCM wind tool wind field or synthetic wind model. And so Bryce Tyner at NC State did a lot of verification work with NDFD forecast and also with the TCM output. And essentially what he found was there was a consistent kind of error that occurred both an over-prediction across most of the quadrants and specific issues in the different quadrants themselves. So in the little cartoon to the right, this is for Ike. What you see here is a crude depiction of what the TCM TCM product would produce in terms of wind speeds. In the upper right is actually the H-wind analysis, and this is a product developed by the Hurricane Research Division. So this is essentially our verification of what the wind field was like at that time. In the lower left is the modified Rankine wind field. This is essentially what is used in the TCM wind tool itself. This is what your tool would give you. And the lower right is the error function added to that, which tends to, or tries to remove some of the typical bias with the actual modified Rankine wind field used in the past. So we've messed around with this a little bit, but we haven't had a chance to get this into the TCM wind tool to evaluate. And this is something where there's probably a lot of verification work that's going to be needed and proof of concept type stuff, but this is another result of our project. So just to sum up real quick, we've worked on a couple experimental methodologies that try to use empirical data to improve this process. We think there are lots of advantages. There certainly are some disadvantages in terms of a new grid and some additional workload, but we think the end result is a more consistent, hopefully accurate and science-based forecast. We've been testing this at a couple WFOs in the southeast. We got to use it during Tropical Storm Andrea early in the year, and we had some positive results from that. And some of the other results of this project are hopefully working their ways into the Tropical Professional Development Series training. Lots of folks need to be acknowledged, and they're on the screen there, including Bryce at NC State and the rest of our CSTAR Tropical Cyclone Wind team. We had various NC State volunteers also help us out with the data collection. Some GP help from some of our neighbors as well, and as well as some other folks who helped out. And we have some references, and at this point, I'd be happy to answer any questions.
Hey, this is Todd Boise up at Caribou. I got a little question about the methodology. What did you do for the land obs in which the stations like the ASOSs didn't report Gust? Because, of course, ASOS doesn't always report the Gust. There's always some factor there, but you don't always know what it is unless it's showing the Gust. So what did you do in those obs where it was just a sustained?
Yeah, that's a good question. I didn't mention that we reduced, or we filtered out all the observations less than 10 knots just to get rid of that noise. As we went through the data set, if there wasn't a gust there per se, then that was excluded from the actual overall data set. We did go back and try to see if there were any patterns there, any issues there that showed up frequently for particular sites or storms. And it was kind of a crude check, but we didn't see anything that jumped out at us a great deal. There's some of the AWASs were in particular a little bit worrisome with the issues there in terms of the quality, but we just used the hourly observations, not the specials, and took the close